be monitoring Slack. I'll be monitoring Slack channel and the channel here. So let's ask the questions at the end of the talk. Thanks. The floor is yours.
Yeah, hello. First of all, I would like to say that I'm very happy for the opportunity to present our work at MLQ. And a special thanks to Christian Bonato for inviting me to give a talk. The evolution of chess mastery is my favorite example of how our approach to problem solving has changed over the past years and how it's still changing. While only 30 years ago, the strongest chess playing entity was still a human, this has changed with time. First, computer programs which have been programmed based on human chess understanding became stronger than humans. However, even though they would make less mistakes than humans, it was clear that they also had weaknesses humans didn't have. It was only in 2017 that computer programs made another leap forward when DeepMind presented AlphaZero, a neural network-based algorithm that learned to play chess by self-play in a few hours. AlphaZero turned out to be stronger than any existing program, and not only that, AlphaZero showed the type of ideas and understanding which previously was still considered to be a human domain. Today, I want to talk about how quantum sensors could profit from a similar evolution. An evolution which started with us understanding and designing quantum experiments, which continued with us programming computers to help design quantum experiments, and at the end of which artificial intelligence learns to understand and design quantum experiments on its own. First, I will set up the problem considered in this talk by introducing Bayesian quantum parameter estimation. Then I show how reinforcement learning can in principle be used to solve this problem of designing quantum experiments for quantum parameter estimation. And finally, I show numerical results for some examples, including frequency estimation of a qubit. And we show that our neural network-based method outperforms the best experiment design heuristics. Quantum metrology is a framework and a method for inferring one or multiple parameters from an environment. Let's say theta is the parameter we want to estimate. Then the idea is to use a quantum sensor, which means a controlled quantum system which exhibits dynamics which depends on the parameter theta. From the measurement outcomes, we compute an estimate of theta. Usually one takes a frequentist approach to parameter estimation. Characteristic for the frequentist approach is an experiment which is repeated many times and some post-processing of the collected measurement outcomes. One of the downside of the frequentist approach and its statistical tools is that its regime of validity is usually that of almost perfect knowledge about theta and many, many repetitions of the experiment. This allows interesting fundamental insights, but often is not very practical, especially when considering the limitations of currently available quantum technology. For example, when the number of experiments that we can perform in a certain time interval is limited, the Bayesian approach to parameter estimation comes in handy. Rather than collecting the measurement results from many experiments, one computes a Bayesian update of our knowledge about theta every time new data is acquired. This opens up the possibility for adaptive feedback after every experiment. Depending on our available information, for example, our knowledge of the theta, we can change the design of the experiment in order to improve the overall precision of the parameter estimation. Let's consider an example. Assume that we have a spin-1/2 particle precessing in a magnetic field, and we want to estimate the precession frequency, omega. In order to do this, we perform several experiments, which consists of preparing a fixed initial state, letting the spin precess for a certain time before we measure a fixed component of the spin, let's say with possible measurement outcomes 0 and 1. Further, we assume that we do not have any particular knowledge about omega, other than that omega lies within a certain interval. This knowledge can be represented by a flat prior over that interval called. And we need to figure out how to update our knowledge. Of course, the update rule is Bayes' law. It takes our current knowledge about omega encoded in the prior and the outcome of the last experiment together with our knowledge about how the quantum sensor works, which is encoded in the likelihood, and returns the posterior, which is the updated knowledge about omega. And the posterior will be the prior for future experiments. Then we are ready to go. We pick some precession time, 0.2, measure and obtain some outcome, update our knowledge. This can be repeated several times. If we are done, we obviously can compute some estimate from the posterior distribution, usually by computing the expected value of omega. As you may have noticed, we picked the same precession time for all experiments. However, experiments tend to become uninformative if you repeat them many times. Alternatively, we can do what is called adaptive parameter estimation. We take available information, such as our knowledge about omega and about the last experiment, and think about how to design the next experiment, means how to choose the precession time. And we repeat this procedure several times. This is called adaptive experiment design. More formally, decision-making concerning the experiment designs is governed by a function called experiment design heuristic, which maps available information to experiment designs, such as fixing the precession time for our experiment. We will come back to frequency estimation, but first we define the general problem of adaptive experiment design. Generally, we have some experiment designs E, some outcomes D, and we want to estimate some parameter theta. Similarly, we can consider the estimation of multiple parameters by considering multidimensional probability distributions. And generally, our objective is to find best experiment design heuristic. To be more precise, we first define what are the available resources for the design of experiments, such as the available time, the allowed number of experiments, or the set of quantum states we are able to prepare in the lab. Next, we need a figure of merit, which is given by the Bayes risk, which roughly speaking is the averaged uncertainty in the final probability distribution of theta. Then we can formulate our objective as finding the experiment design heuristic H, which minimizes the Bayes risk using the available resources. The iterative scheme of designing and performing experiments can be depicted like this, involving the experiment design heuristic, the quantum experiment, and a numerical Bayesian update. There exist efficient solutions for the numerical Bayesian update using a sequential Monte Carlo method. In particular, there's the well-documented Python package Q-infer, which already provides all the tools we need. Therefore, let us focus on experiment design heuristics. Obviously, we could use a computer program to run a numerical optimization, determining the next experiment. But a typical timescale of quantum experiments is very short, such that the lengthy computation between experiments would ruin the overall performance of our quantum estimation procedure. And not only that, assuming that we only have to choose the next experiment design would be greedy optimization. Instead, we are interested in finding a policy for choosing an adaptive sequence of experiments using certain resources, such that the Bayes risk becomes minimal in the end. This means we are looking at a much more complicated global optimization problem. This problem can be tackled when formulated as a reinforcement learning problem. The first step is to model the experiment design heuristic with a neural network. And then we consider everything except the neural network as the reinforcement learning environment, depicted as the shaded gray box. The learning agent will be represented by the neural network. Its observation is the available information about resources, about data, about past experiments, and its action will be the experiment designs. The agent will interact with the reinforcement learning environment until the resources are expired, and this corresponds to one estimation run called episode in the reinforcement learning language. At the heart of formulating a problem in the language of RL is defining the reward, which will be used by the agent to improve its behavior. Obviously, we'd like to define the reward such that reinforcement learning ultimately minimizes the bias risk. We cannot directly use the Bayes risk for the reward because its computation is too time-consuming. Instead, we define the reward as the change in variance of the probability distributions for theta, defined here for the multiparameter case via the trace of the covariance matrices. And this is a clever definition for a reward because on average, the expected accumulated reward, which reinforcement learning tries to minimize, equals the negative Bayes risk. So effectively, reinforcement learning minimizes the Bayes risk. First, we consider a simple evolutionary strategy. So in this reinforcement learning framework, we can use several algorithms, and one of the algorithms is this cross-entropy method, which shows a remarkable performance for our problems. Unfortunately, I don't have the time to go into the details of the algorithm. As a second algorithm, we consider a full-fledged reinforcement learning algorithm called trust region policy optimization. It is one of the most successful reinforcement learning algorithms for the standard benchmark problems. It's available via the Python package, stable baselines. And we improve its performance using imitation learning, where the neural network is initialized by training the neural network to imitate some existing heuristic. So we show some episodes and use imitation learning to initialize the neural network, and only then, when the neural network has been initialized, we apply TRPO to further improve the performance of the heuristic. In the following, I will present some numerical results. We considered the same problem of frequency estimation with a qubit, but this time we also considered some variations. Besides the previously considered unitary version, which we will call problem 1, we also considered dephasing as a decoherence mechanism, which will be problem 2. And finally, we also consider multiparameter estimation, where we estimate both the frequency and the dephasing rate. In our paper, we considered two different resource limits. One, where the total time is fixed, but the agent can perform as many experiments as it wants. And one where the total number of experiments is fixed, but the agent is free to consume as much time as it wants. Here I just present the results for the time-limited case. The results for the experiment-limited case are very similar. On the x-axis, you can see the time where the maximum value t equals 100 is the total available time for one run of the estimation, which means one episode. Along the y-axis, we plot the numerically computed Bayes risk. The different lines correspond to different experiment design heuristics. We consider 3 benchmark heuristics, from which x bars is the only non-adaptive heuristic. I don't have enough time to explain heuristics, but I give the reference below. Also, those heuristics have previously been used in experiments. The new heuristics found in our work correspond to the yellow and the red lines, corresponding to the cross-entropy method and trust region policy optimization, using the heuristic in brackets as a pre-training step. We can see that a neural network heuristic found with TRPO achieves, together with the X-bars heuristic, the best performance, which means the smallest bias risk, where the cross-entropy method performs almost as good. Let's look at the next example, where we consider frequency estimation, but this time With the phasing, we defined that our neural network heuristics, the red and the yellow lines, perform much better than the benchmark heuristics. CAPO achieves an advantage over the benchmark heuristics by more than 1 order of magnitude. Next, we consider an example of multiparameter estimation, where we want to estimate both the frequency and the dephasing rate. We find that a partly death heuristic in blue does a pretty good job here, but our neural network heuristics perform even better. Now you may wonder how the experimental signs chosen by the heuristics look like. This is difficult to visualize and understand because of the adaptivity of the heuristics. One way is to look at the times here on the y-axis chosen for the nth experiment. The experiment number is depicted on the x-axis. And basically, the takeaway message is that there's a huge variety in the behavior of different heuristics. And doing these plots for different estimation examples only adds to this variety further. So let us summarize. We introduced the idea of smart quantum sensors within the framework of adaptive Bayesian parameter estimation. We established a general framework based on reinforcement learning, which can in principle be used for all kinds of adaptive quantum sensors. And we show that neural network heuristics outperform state-of-the-art heuristics in our examples. As an outlook, there are several things which could be tried. Obviously, one can try to improve the reinforcement learning step by improving the performance of the algorithm by studying the robustness of the RL agents, for instance, if they have to act in an environment which they didn't experience during training, or how it generalizes to larger problems. And we could also look at related problems, which is not only the standard parameter estimation problem, but also some detection of time-dependent signals or state tomography. And one could also go towards quantum information processing, where everything would be computed on a quantum processor chip. So the Bayesian update and the RL agent would be computed on quantum hardware. And finally, obviously, it would be exciting to test neural network heuristics in experiments. Thanks a lot for your attention.
Thanks for the very nice talk. I think we have some time for a few questions. So if you have some questions, you can type it on Slack or type it here and I will relay it to the speaker. So we have one question already from Timo. And he asks if the PGH has been shown to operate close to standard quantum limit. Have you compared your heuristic against the SQL?
I'm sorry, PGH has been shown to. Okay, yeah, so I'm not exactly sure I get the question because I consider the standard quantum limit as a term related to frequentist approach to parameter estimation mainly. So here we are doing adaptive parameter estimations. I'm not exactly sure what SQL means in that context, to be honest.
If Timo has anything, maybe he can type and I'll relay it. But maybe meanwhile, I have one question of myself. So, okay. Before my question, there's a question by Brian. Is the neural network heuristic expected to perform as well as the increasing complicated likelihood functions?
Yeah, that's a good question. Obviously, we need the likelihood function in order to do the numerics. So at every step, the likelihood functions are used, and the runtime for one call to the likelihood function determines the performance of our algorithm. So for our example, we had a very simple likelihood function, which was given by a very simple analytic formula. But if the likelihood function becomes more complicated, obviously also the reinforcement learning part becomes more time consuming. But one has to say that if the likelihood is more complicated, also the Bayesian updates become more complicated. So I don't think that reinforcement learning is is here the limiting factor, but I think it's the Bayesian update, because we need the Bayesian updates anyway. And if the likelihood is too complicated, then Bayesian updates will be very slow, and it doesn't really matter if reinforcement learning is working or not, if the Bayesian updates won't work.
Timo has a comment in his question. Like, maybe you can take a look quickly and see if that answers your question.
There's a follow-up question like from Brian. Models with more parameters where usually PGH can perform okay. Do you think this approach will still beat PGH? Yeah, so indeed we observed that PGH performed well for our 2-parameter estimation. But I don't know, I haven't tested it for more than 2 parameters. So it's hard to say. Just hard to say. I think the framework applies obviously also in the multi-parameter case for more than 2 parameters, but it's hard to say whether it will be better than PGH.
So let's take one more question by Guido. So he asks, if I understand correctly, it's adaptive sensing is stated here as being used between experiments. So measure the first T0 time, 1,000 times, get expectation value, and then determine the T1 to measure. Can this also be done within one measurement with repeated weak measurements?
Yeah, actually, I'm kind of in the measurement frugal regime here. So we only consider single measurements. So not 1,001, but just one measurement with one outcome. And then we perform an Bayesian update. But obviously, you could also consider several measurements and only then perform an update. And for the multi-parameter example, I actually did this in order to speed up the estimation of the dephasing time. I had to increase the number of experiments, and what I did, I indeed always did 100 times the same experiment, and only then I performed an Bayesian update. So can this also be done within one measurement with repeated weak measurements? Decide T1 on the basis of the first bit measurement. I'm not sure I get the second question completely, to be honest.
But maybe we should also take this off on Slack. Like we should get this next speaker set up and things.
Okay.
But I'll copy these questions onto Slack, and maybe you can reply to them on Slack in your channel.
Okay. Very good.
Yeah. Thanks again. Yeah, that was great. Yeah. Let's go let's set up the next speaker now. Yeah. Thanks.
Okay, so I'm happy to answer the questions in Slack. I don't know, maybe I can copy them or something. Okay.
I will copy them down.
Okay, thanks a lot. Thanks. Let me.
Okay, we have the next.
Maybe before we start the video, I can say a couple of words.
Sure.
Yeah, just to make it a bit easier for the audience to understand. So my talk is pre-recorded, but it will actually be very similar to what we just saw by Lukas, with the difference that the likelihood that I focus on the form of the likelihood function rather than its specific parameters. So I take out all the neural network machinery that Lukas just presented and replace it with something very, very simple, humanly easily understandable, and rather focus on the shape of the function and let's see how to design that heuristic manually, really, by trying things out by hand. And otherwise, it's quite related to what you just heard.
Okay. Anyways, Kirill will present his pre-recorded talk. If you have any questions, again, present both on Slack or here, and I will relay to the speaker at the end of the talk. Yeah, you can begin.
Hello. My name is Kirill Streltsov. I'm a PhD student in Martin Plenio's group. I would like to tell you about a sensing scheme that we developed for a ground state cooling protocol of a levitated magnet. We consider a magnet levitated above a superconductor that is not shown in this picture. The radius of the magnet is about 1 to 10 micrometers, making it quite large and heavy, and therefore leading to low trapping frequencies. These systems are believed to constitute very sensitive inertial force sensors and useful for fundamental tests of quantum mechanics. However, to achieve that, one needs to reach the quantum mechanical ground state of the center of mass motion of these systems, which is very challenging due to the low frequencies. In fact, existing cooling proposals cannot be applied in this setup. So, in addition to the particle, we also consider a sensor. It might be an NV sensor or any other two-level system that couples to the motion of the particle and can therefore extract some information. Our cooling scheme, is a variation of a feedback cooling, which can be understood in the following way. Feedback cooling has two components. First is state estimation, which provides you some information, and the second step is the feedback step, which extracts energy. Now, this information can really be gained through sensing. It's completely equivalent to sensing, where we start with a thermal state of the particle, and now by sensing its position and momentum, we transform this thermal state into a coherent state, simply by determining the position and momentum with sufficiently high precision that is given by the width of a coherent state. Having done that, we can extract the energy of the particle by a unitary displacement operation that simply means shifting the trap center back to that position. Now, to perform sensing, we of course need to couple our two-level system to the magnet, which we assume to be a dipole, and linearizing that dipole gradient field, we arrive at this linear coupling Hamiltonian. And you immediately recognize the familiar form of it because it's almost identical to standard quantum sensing Hamiltonian. If we would replace this X operator with a real number, some classical field. And in fact, everything that I will tell you now directly translates to quantum sensing of DC fields. The only thing that we have to consider, because this is an operator, is that our sensing scheme can impose back action onto the particle. So we arrive at a list of constraints that our sensing protocol has to fulfill. First of all, we know that the particle is in a thermal state, which corresponds to some knowledge that we have about it. And that makes the setup perfectly suited for a Bayesian inference scheme, where this knowledge corresponds to the prior distribution. Furthermore, we have a two-level system as a sensor, which has binary output, either up or down in each measurement. And the particle is coupled to an environment and therefore experiences heating. That sets limits on the total sensing time that is available to us. And as I just mentioned, we can introduce, or the sensing scheme introduces back action onto the particle, which in fact prevents us from using a Ramsey-based sensing scheme. These two papers that I've listed here pursue similar ideas in terms of Bayesian inference for quantum sensing as our protocol, but they do use the Ramsey sequence, which makes them unsuitable for our purposes. Now, our protocol really focuses on the limited sensing time and achieving sensing in an efficient way. What do I mean by that? To explain that, let's look at the Bayesian update rule. It features the prior distribution here in white, then the likelihood function that depends on the measurement parameters in red, and the final distribution, the posterior distribution, in yellow. Ideally, we would end up in a final distribution which is centered around the true value of an unknown parameter and which has a width that is as narrow as possible, or in our case corresponds to the width of a coherent state. A strategy to get there would be to choose Gaussian, a narrow Gaussian, as the likelihood function. So that would look like this. It seems that we achieve our goal because the final distribution is a narrow Gaussian here, but we need to consider that that outcome is extremely unlikely. Far more probable is the spin-down outcome, and that actually gives us almost no information about the unknown parameter, except that it's not in this position. So that suggests that we need multiple measurements to achieve our goal, and one way to do that would be simply repeat a given measurement, a measurement that has a likelihood function that is monotonously increasing over the relevant range. Then collect the measurement results, compute an average that would correspond to some value here on the red line, and then map that value to the unknown parameter value. But that is clearly not the optimal strategy. The sensitivity of this experiment will be very far away from the Cramer-Rao bound, which is the optimum. So one way to get closer is to introduce adaptive sensing. That means we have another look at the likelihood function, at the total likelihood function, which consists of a product of the likelihood functions of each individual measurement, and optimize this. But in the case, for example, where each measurement can be described by a Gaussian likelihood function, we quickly realize that this is an intractable problem because the number of parameters that we would have to optimize over is 2 to the power of n, n being the number of measurements. So that's 2 to the 10, 2 to the 100, etc. A completely intractable problem. So what one rather would do is create a recipe that gives you the measurement parameters for a given prior distribution. So we would compute them, make the measurement, record the measurement result, apply the Bayesian update rule, arrive at some resulting distribution, and then use that as the prior distribution for the next measurement. And here we are faced with the question of what is the optimal measurement that we can do, or by how much can we reduce the variance of the prior distribution in each measurement. And the answer here is not exactly obvious unless we look at the entropy. Here I've written down the entropy of a Gaussian distribution, which monotonously depends on its width. Here we can immediately see what is the optimum, because we know that we have a binary sensor and that the binary sensor can extract 1 bit of information. So the optimal form for the likelihood function would actually be this step function. Well, this is one of the optimal forms that exactly halves the Gaussian prior distribution in this kind of way, if we center the step around the center of the Gaussian. Now we can also have this distribution. This can be easily computed with an analytic formula, and we can keep doing this halving until we arrive at the desired width. and that would constitute an optimal strategy. So now we have to ask ourselves how to actually implement this with a two-level system sensor. For that, we look at the Hamiltonian, which depends on the unknown parameter x, and contains some driving of our sensor. It can be easily shown that the likelihood function depends in this way on the Hamiltonian. In fact, we refer to it as the inversion profile because that simply corresponds to the population of the excited state of the two-level system. We can now plug in various drivings, for example, Ramsey driving, which would give us a cosine squared dependence. We could plug in a constant Rabi frequency here, which would yield the familiar Rabi formula. And there's also a way to design the driving such that we obtain the step function from the previous slide. However, we notice that the time scale needed to create that step function is determined by the sharpness of the step. And in addition to that, this sharp step introduces a back action on the particle, which is actually detrimental for a protocol. It will ultimately reduce the ground state fidelity of the particle. So, considering that it would take too much time to design that to create that likelihood function, and that it induces a back action, just like the Ramsey scheme, by the way, it introduces a broadening of the momentum distribution. We decided to go with the Gaussian inversion profile, which can be generated by a Gaussian modulation of the Rabi frequency. The parameters for this profile linearly depend on the parameters of the Gaussian prior, and what I've plotted here is the spin-down outcome. And here we immediately see that there's a problem because that's clearly not a Gaussian. So after such a measurement result, I wouldn't know how to compute the measurement parameters for the next step. To overcome this problem, we introduced the thresholding procedure shown here. We have a threshold theta, and because we know the numerical form of our prior distribution, we can compute the intersection with this threshold, thereby arriving at this delta x value. And then we simply determine sigma to compute such that it fulfills this relationship. This is equivalent to simply putting a Gaussian through these 2 points. Now we use that as the effective prior distribution and compute the measurement parameters in the same way as described in the previous slide. So there are a number of other tricks that we have to apply to ensure stability, but for that you can have a look at the paper on the archive. So the results that we arrive at are the following. We see here, very importantly, that the entropy decreases in a linear fashion, just like in the optimal solution, which where the entropy would be reduced by 1 bit in each measurement, and this is also what we see here. However, in our case, for perfect 3-dot fidelities, we obtain an entropy reduction per measurement of 1/4 of a bit. Furthermore, our protocol works also for finite 3-dot fidelities, and then correspondingly with a correspondingly reduced slope here, because we simply have we extract less information with each measurement. But I stress again that this shows that the protocol is very close to optimality, because it ensures that in each measurement equal amounts of information are extracted, and that the protocol never gets stuck in some kind of way where basically only very little information gets extracted. And what I have shown you here is not an average over many kind of measurements. It's really a single measurement run, and they all look exactly in this way. Now, on the right side, I plot the entropy as a function of time. Unsurprisingly, this is not a linear relationship, because the width of the distribution decreases with each measurement, and therefore the required resolution becomes larger and larger, and that's basically what we see here, that each measurement requires more and more time. So we set out to design this protocol for a certain goal, for achieving the ground state of a levitated mesoscopic particle. And here I show you that we were actually successful in this goal. What you see here is the ground state fidelity of the particle as a function of readout fidelity of the sensor for different thermal initial excitations, for different thermal initial occupations. This can go up arbitrarily high. You see that the curves overlap, and we say that this protocol can be even applied for at room temperature, where this number is roughly 10 to the power of 10. Of course, the performance gets degraded with reduced readout fidelity, but anything above this shaded area corresponds to less than 1 thermal excitation. Now, I hope I have convinced you that entropy reduction is a measure of the optimality of the measurement, and that you can generate optimal measurements by suitably driving this sensor and creating shaped inversion profiles. I've shown you an example of this approach, which can be used to reach the motional ground state of a levitated particle. And however, there's one more open question, and this is: what is the inversion profile that extracts most amount of information per unit time? We have so far more looked at the number of measurements rather than really finding the optimum in terms of time. However, we believe that our scheme is actually already very close to that. So with that, I'm at the end of my talk, and I would be happy to answer any questions that you might have. Thank you very much for your attention.
Thanks for the talk. Yeah, I think we have time for a couple of questions, just to keep in line with the schedule. If anybody has questions, feel free to type it on Slack or post it here, and I can relay it to the speaker. Maybe until people ask, let me ask one question of my own. So is there any way you can, even for small experiments, provably show that this entropy reduction is the right way to get the optimal measurement?
Well, I would say the kind of the guide that we have towards what is optimal, what is not, is really the property of a sensor. And due to the fact that we know that we have a binary sensor in this case, I would say that yes, seeing that the entropy is reduced by 1 bit is let's say an objective statement about whether that's optimal or not. So I would like something that just gives you 1 bit of information cannot reduce the entropy by more than 1 bit. Now, whether that would actually achieve your goal of that is usually having a narrow posterior distribution, that is a bit that depends a lot on the heuristic itself. So I have shown you this thresholding procedure, and that's exactly there to prevent a development of, let's say, multiple peaks in your distribution. Because if you would have that, you would have, I mean, you would definitely need to adapt your heuristic to still be able to extract 1 bit. So your algorithm might maneuver itself into a place where your distribution, your prior distribution is so complex that that you would have to design a similarly complex likelihood function to be able to extract one bit of information. And that's simply not obvious. So that's exactly what we were looking at here, to keep things simple, to have the heuristic designed in a way that the distribution is always close to a Gaussian, and so that this reduction in one bit is achieved in every measurement. And of course, that we also end up in a Gaussian state at the end. Because if we would not get there, then obviously our ground state fidelity would be low, because it simply wouldn't be a Gaussian state.
Correct. I see. Okay, that makes sense.
I mean, in a sense, it's a bit related to what Timo asked in the previous talk about like the standard quantum limit. I agree with Lukas that basically it's not obvious how to relate a Bayesian scheme to the standard quantum limit that relies on frequencist approach. And I would say that rather than looking at that, one should look at the entropy, or in fact also at the base risk. Though there again, depending on the function of the risk. So in my case, it would be, for example, be the fidelity. It's also not so obvious how your what your sensor can do. In case of entropy, really, the properties of your sensor determine the optimality there.
I see. Thanks. I think yeah, schedule says we're a couple of minutes overdue already. So I think if anybody has further questions, they can ask it on Slack and maybe you can reply there. But for now, I think we don't have any further questions and maybe we should adjourn the session. So we'll be back in 40 minutes for a tutorial by Alan as per Guzik. So hope to see you all there.